All right, good morning. So last time we actually sort of looked at two methods, which were the so-called the began method and the two-phase method. And remember, so these were methods that help you find the initial basic feasible solution of an LP problem when you solve the problem with the simplex method, given that the problem does not have a readily available initial basic feasible solution to start with. And then, we saw different examples, and we sort of realized that actually the two methods behave differently in some sense. So now we're going to move on to a new topic called duality. So this is one of the last topics in this course, one of the most important as well. And this is also important for your projects as well, okay? So you will also have to answer some questions regarding duality in the projects. So let's start with the generic LP problem. So consider the following LP problem. So remember, we can represent an LP problem by using vectors and matrices. And for now, I'll just assume that I have less than or equal to constraints, okay? So, and we know how to convert it into standard form, so we just need to add slack variables to the problem. So remember here, C and X are two vectors. C is a row vector and X is a column vector. A is a matrix. A times X is a vector, and B is a vector as well. So the inequalities basically are component-wise inequalities. So a vector is, each component of the vector on the left-hand side is less than or equal to corresponding component of the vector on the right-hand side. So now I'm going to ask you the following question. So the question is, how can we obtain an upper bound on the optimal value without actually knowing it? So essentially, my question is the following. So I have an LP problem, which may be in this form in general. Okay. And my question is the following. So suppose that I want to solve this problem, okay, and suppose that this problem has an optimal value. And the question is the following. So what I'm trying to do is I'm trying to find an upper bound on the optimal value. What does that mean? So, I'm not really interested in finding the optimal value, but I want to know that the optimal value, let's say, cannot be larger than 500 or something like that, okay? So the question is, without knowing what the optimal value is, how can I say that the optimal value cannot be larger than a certain number? So how can I find an upper bound on the optimal value? Let me give you an example. So suppose that we have the following LP problem. So I would like to maximize x1 plus x2 plus all the way up to, let's say, x100. So let's say I have 100 decision variables. And then I have two constraints. So the first one goes as follows: x1 plus 2x2 plus all the way up to 99x99 plus 100x100. And I want this to be less than or equal to 1. So essentially, think of the constraint as x1 plus 2x2 plus 3x3 plus 4x4 and so on and so forth. Okay, so the coefficient of each variable is the same as the index of that variable. And then I have a second constraint. So think of the coefficients of the second constraint as, take the coefficients of the first constraint and repeat it in the other direction. So starts with, 100x1, 99x2, 98x3, and so on and so forth, okay? So one way to think about this is the coefficient plus the index is always equal to 100 or 1. So 100 plus 1 is 101, 99 plus 2 is 101, 2 plus 99 is 101, and 1 plus 100 is equal to 101. Okay? So all I'm doing is I'm just sort of changing the order of the coefficients. And then each of my variables is non-negative. So if I give you such an LP problem, then you know how to solve this problem, right? So you will just add slack variables, turn it into standard form, and you're going to apply the simplex method. So we can start with the slack variables as the basic variables, so we don't need to introduce artificial variables for this problem. So essentially, we can solve this problem, right? Okay. However, let me just go back to my question again. So, without solving this problem, okay, so I don't want to solve this problem right now, but without solving it, I want to say that the optimal value cannot be larger than a certain number, for instance, okay? I want to say that the optimal value cannot be larger than, let's say, 1,000 or 2,000 or something like that, okay? So my question is the following. So if I have such an example, then how can I say that the optimal value cannot be larger than a certain bound, cannot be larger than a certain value? Or can I say it for this problem? So let me open my question again. So what I'm interested in is the following. So I have an LP problem such as that one. And what I want to do is I want to say that the optimal value, I don't know what the optimal value is, but I want to say that the optimal value cannot be larger than a certain number, for instance. Okay? So the question is, how can I do that? Yes? Okay. That's a great idea, basically. So what your friend is suggesting is the following. So if I look at the constraints, okay, now every feasible solution should satisfy all of these conditions, basically, right? By definition of a feasible solution. So if a feasible solution satisfies the first constraint and also satisfies the second constraint, then it should also satisfy the sum of these two constraints as well, right? So if I have a solution that satisfies the first constraint, and if I have a solution that satisfies the second constraint as well, then that solution should also satisfy the sum of these two constraints as well, right? Is that clear? Okay. So as a result, basically, we can make the following claim. So the claim is that the optimal value, I don't know what that is, but I know that the optimal value is always less than or equal to 1. Okay. And why is this true? Well, so every feasible solution should satisfy all the constraints by definition, right? And in particular, it should satisfy the first two constraints. Okay? So let me call them 1 and 2. So in particular, it should satisfy 1 and 2. So 1 refers to the first constraint, and 2 refers to the second constraint. And as I said, well, if I have a solution that satisfies the first and second inequalities, then that solution should also satisfy the sum of these two inequalities as well, okay? So then every solution, every feasible solution, should also satisfy the sum of 1 and 2. Well, so let's see what happens if I sum the first and second constraints. Well, if you sum the first and second constraints, you have 101x1 plus 101x2 all the way up to 101x99 plus 101x100. So these are the coefficients, okay, on the left-hand side. What about the right-hand side? Well, the right-hand side is also 101, basically, right? Okay. So once again, the crucial observation is the following. So if every feasible solution satisfies the first and second constraints, then every feasible solution should also satisfy this constraint as well, okay? Because this constraint is driven by the constraints of the original problem, okay? If I have any solution that satisfies the first and second constraints, then that solution should also satisfy this constraint as well. So think of this as an implied constraint, okay? All right, so then what I'm going to do is I'm going to just divide everything by 101, and then I get x1 plus x2 plus all the way up to x99 plus x100 is less than or equal to 1. So, well, this is important, okay? So I don't know what the optimal value is, okay? However, I can say that without knowing what the optimal value is, the optimal value cannot be larger than 1, okay? So let me repeat that again. So right now, I haven't solved that problem. I haven't solved the LP problem. But what I do know is that, so regardless of what the solution is, the optimal value can never be larger than 1. Does everybody see that? So essentially, if I go back to my question, I actually achieved the bound on the optimal value, right? So I don't know what the optimal value is, but I know that the optimal value cannot be larger than 1. Okay? So why is this important? Well, so essentially, think of this as a production planning problem, for instance. Okay, so I have 2 resources, and I want to maximize my profit. Okay, and what I'm interested in is finding an upper bound on the profit. So, for example, I know that from this production schedule or production problem, my profit can never be larger than 1. So whatever the unit is, okay, $1 million or whatever. Okay, so as a result, without solving the problem, I can tell you that I can never make more than 1 million, for instance. Okay, on this problem. Okay, so now let's try to understand what exactly we did. So what did we do exactly? So what did we do to obtain the upper bound of 1? Well, so when we think about this is the following. So I take the first constraint. Okay. I take the first constraint and I multiplied it by 101. 1 divided by 101. Okay, both sides of the inequality will be multiplied by 1 over 101. Similarly, I'm going to take the second inequality and multiply it by 1 divided by 101. Okay, and add them up. Well, let's see what happens if we follow these steps. So I'm taking the first inequality and multiplying it by 1 over 101. Okay? So the constraints, the coefficients become 1 over 101 plus 2 over 101 plus 3 over 101, so on and so forth. All the way up to 100 over 101 is less than or equal to 1 over 101, right? So that's exactly what happens if you multiply the first constraint by 1 over 101. If I do the same thing on the second constraint, again, the coefficients become, 100 divided by 101 plus x1 plus 99 divided by 101 plus x2 times x2, 2 divided by 101 times x99, and 1 divided by 101 times x100, and right-hand side becomes 100 divided by 101. And if I add them up, it's not too hard to see that you get exactly this inequality, basically, right? Okay? If you add up to 2, then you get exactly that inequality. And the nice thing about that inequality is that if you look at the left-hand side of the inequality, that's exactly the same as the objective function, basically, right? Okay? So we know that every feasible solution that satisfies these 2 constraints should also satisfy this inequality as well. So every feasible solution should necessarily have the property that if I sum up all the components, that should be less than or equal to 1. But that's precisely my objective function, right? So my objective function is precisely the sum of all these variables. So as a result, essentially I know that without knowing what the optimal value is, I know that the optimal value cannot be larger than 1. Okay? Questions so far? All right. So now the question is the following. So now how can we turn it into a sort of general procedure? Okay, how can I generalize this? So this was just this example. So the question is, how can we generalize this idea? So which idea? Well, the idea of finding an upper bound on the optimal value without solving the problem. Okay. So I want to come up with a procedure that would give me an upper bound on the optimal value without knowing what the optimal value is. Okay, just like we did on this example. So for that, I'm going to look at the general LP problem. Okay. So let us consider the following general LP problem. So suppose that I want to maximize C1x1 plus C2x2 all the way up to Cn times xn. And then I have my constraints given by A11x1 plus A12x2 all the way up to A1 and xn is less than or equal to B1. So this is my first constraint. Then I have my second constraint, A21 times x1 plus A22 times x2 all the way up to A2n times xn is less than or equal to B2. Finally, AM1 times x1 plus AM2 times x2 all the way up to amn times xn is less than or equal to bm, and each of my variables is non-negative. So this is a general LP problem, basically. Okay. So I have m constraints, m less than or equal to constraints. I have n variables. I have my objective function. In addition, I have m less than or equal to constraints, and I have n non-negative variables, right? For example, this problem would be in that form as well, right? So this problem is in the same form with m equals 2. Okay. So we have only 2 constraints for this problem, and n equals 100. All right. So now this is important. I just want you to pay attention. So if I go back to the previous example, what did I do? Well, I took the first constraint and multiplied by some non-negative number. Okay. I took the second constraint and multiplied it by some other non-negative number, which happens to be the same in this case. And then I added up the constraints. Okay. Well, so if I try to generalize this idea, well, I can take the first constraint and multiply it by any non-negative number. Now, non-negativity is important because I want to actually preserve the sign of the inequality, the direction of the inequality, right? If I multiply by a negative number, then the inequality will change direction. Okay? Does everybody remember that? So if you multiply an inequality by a negative number, the inequality changes direction, right? Okay? So I want to preserve the same direction. So as a result, I need to pick a non-negative number. So I'm going to pick a non-negative number to multiply the first constraint, to pick another non-negative number to multiply the second constraint, and so on and so forth. And I'm going to pick another non-negative number to multiply the last constraint. Then I'm going to add them up. Okay? And that will give me a single inequality, basically, right? So I'm just going to take the first inequality, multiply by some number, take the second inequality, multiply by some number, and I'll just do the same thing for each of the constraints. And if I add them up, I will get the left-hand side is less than or equal to some right-hand side value, right? Just like we did over there, right? Okay? All right, so essentially what I'm going to do is the following. I'm going to call W1. So W1 is the multiplier for the first constraint. Okay, W2 is the multiplier for the second constraint, and Wm will be the multiplier for the last constraint. Okay? So what I'm going to do is I'm going to multiply each constraint by the corresponding multiplier, and I'm going to add them up. Okay, and let's see what we have. So let me pick W1 greater than or equal to 0, W2 greater than or equal to 0, all the way up to Wm greater than or equal to 0. So let us multiply each constraint by the corresponding multiplier. And add them up. So now this is, you just need to be careful here. So basically, the number of multipliers that I'm going to use is the same as number of constraints, right? Number of less than or equal to constraints. So I have m constraints, I have m multipliers. In the previous example, there were only 2 constraints, and I just used 2 multipliers, okay? So think of this as W1 and W2, basically, okay, in this example. So as I said, I'm going to multiply each constraint by the corresponding multiplier, and I'm going to add them up. Okay, and if I add them up, then I can write it in this way. So x1 will have a certain coefficient, x2 will have a certain coefficient, and so on and so forth, right? Okay. So the question is, what exactly is the coefficient of x1 in the summation? So x1 will be multiplied by W1A11 plus W2A21. Okay, this sounds good. All the way up to Wm times Am1, basically, right? So Wm times Am1. So this will be the coefficient of x1. Okay. What about x2? The coefficient of x2? W1 times A12 plus W2 times A22 plus all the way up to Wm times Am2, right? Wm times Am2. And I'm going to multiply it by x2 plus, I'm going to have some other components. Let's write down the coefficient of xn, the last variable. So I'm going to have W1 times A1n, right? So now I'm just looking at the last column, basically. Okay. W2 times A2n, all the way up to Wm times Amn. I'm going to multiply by xn. Okay. Now, what about the right-hand side? So this is the left-hand side, basically. Okay. What about the right-hand side? W1b1 plus W2b2, all the way up to Wm times Vm. Okay, so let's just stop for a minute and let's try to understand what exactly we're doing. So essentially, I have m constraints, m less or equal to constraints, and for each one of them, I'm actually picking a non-negative number. Okay, so I haven't told you what these numbers are yet. Okay, so these are, think of this as any non-negative numbers. So for example, in the previous example, think of this as my W1 and this is my W2, basically. Okay, so these are the multipliers, and then I'm adding each constraint with the corresponding multiplier. And then I'm adding up the resulting inequalities, and that gives me a single inequality, which is expressed in that expression over there, right? Okay? So as a result, think of it this way. Every feasible solution of this problem, okay, should also satisfy that inequality as well. Why is that? Because every solution that satisfies all of these inequalities should also satisfy that inequality, because that inequality is derived from these inequalities, basically, right? Okay? So as a result, every feasible solution should also satisfy that inequality. Okay? So now the question is the following. So, well, how can I use this to find an upper bound on the optimal value? Okay? Well, this is important. So far, I haven't told you how to choose W1 through Wm yet. So far, for every choice of W1 through Wm, that inequality is true, basically. Okay? However, what I want is, I want that inequality to give me further information about the objective function. Okay? So, and if I want that, I need to pick my W1 through Wm in a careful way, basically. Okay? And this is exactly what we're going to do now. So therefore, if we choose the multipliers, W1 through Wm, so what I'm going to do is the following. I'm going to look at the coefficient of x1. Okay? So W1 times A11 plus W2 times A21 plus all the way up to Wm times Am1. Okay? So this is precisely the coefficient of x1, which depends on w's and ai's, basically, aij's. Okay? And I want this to be greater than or equal to c1. What is c1? c1 is precisely the objective function coefficient of x1. Okay? Then I'm going to look at the second, the coefficient of x2. So W1 times A12 plus W2 times A22 plus all the way up to Wm times Am2. And I want this to be at least c2. c2 is the coefficient of x2 in the objective function. And I'm going to continue. And I'm going to look at the coefficient of xn. So W1 times A1n plus W2 times A2n plus all the way up to Wm times Amn. And I want this to be at least as large as Cn. Now let's try to understand what we're doing exactly. So I'm free to choose W1 through Wm, whichever I like, basically, okay? And regardless of what I pick for W1 through Wm, this inequality is always satisfied. So this is always true, okay? So now what I'm doing is the following. I'm actually not picking W1 through Wm in an arbitrary way, but I'm actually picking them carefully, so to speak, okay? And what do I mean by carefully? Well, rather than picking them, randomly, I'm going to pick them in such a way that all of these conditions will be satisfied, okay? So I'm going to pick my W1 through Wm in such a way that when I evaluate this expression, I want it to be at least as large as C1, okay? Similarly, I want this expression to be at least as large as C2, and I want this expression to be at least as large as Cn, okay? Note that all of these expressions depend only on W's and Aij's, right? Only my coefficient matrix A and only my W's, nothing else, okay? So if I can choose my W1 through Wm such that all of these are satisfied, then I claim that I can use this to find an upper bound on the optimal value of my problem, okay? How can I do that? Well, let me just go back to the previous inequality. So the left-hand side is less than or equal to this right-hand side value, right? Okay? Now suppose in addition that these inequalities are also satisfied, okay? Now if these inequalities are satisfied, please pay attention here, so this is important. So this is precisely the coefficient of x1, right, in this expression. Okay? So this coefficient, I know, is at least as large as c1. Okay? So which means that the first entry here, the first term, this coefficient times x1, should be at least as large as c1 times x1, basically, right? So if I multiply both sides by x1, then this times x1 should be at least as large as c1 times x1, because x1 is non-negative. Okay? Similarly, if I multiply this by x2, so this times x2, which is precisely the second term, is at least as large as c2 times x2. Okay? And finally, if I multiply the last one by xn, then this times xn, which is the last term, is at least as large as cn times xn. Okay? So what does that mean? Well, if I look at this expression here, this expression is always less than or equal to this expression. And this expression in turn will be greater than or equal to c1 times x1 plus c2 times x2 all the way up to cn times xn. Okay? But c1 times x1 plus c2 times x2 all the way up to cn times xn is precisely my objective function, right? Okay? Well, that means that now this will be an upper bound on the optimal value. Okay? So that's exactly what we were trying to do. Then we have c1 times x1 plus c2 times x2 all the way up to cn times xn will be less than or equal to w1b1, w2b2, all the way up to wmbm. So of course, I mean, right now, I haven't told you how we're going to choose w1 through wm so that these are satisfied. But if we can do it, okay, then that will give us an upper bound on the optimal value. Does everybody see that? Okay. So if I choose my w1 through wm carefully, then I can always obtain an upper bound on the optimal value of this problem without knowing what the optimal value is. Okay, that's important. So I don't know what the optimal value is, but I know that the optimal value can never be larger than this expression over here, for instance. Okay? And note that this expression only depends on w's and bj's, basically, right? Only w and b. Okay? So this implies that if we choose w1 through wm carefully, then we can obtain an upper bound on the optimal value, and without actually knowing it. Okay? So once again, I still haven't told you how we're going to choose w1 through wm so that these are satisfied. But suppose for now that we can somehow choose values w1 through wm. And if I pick my w1 through wm carefully, and carefully basically means that so that all of those inequalities are satisfied, then I can always obtain an upper bound on the optimal value of this problem without knowing what the optimal value is. So that's important. Okay? Questions? Okay. Now, please continue to pay attention because this is really important. So suppose that there's a particular choice of w1 through wm, and all of these are satisfied, and that gives me this upper bound, basically, right, on the optimal value. And if you think about this in general, so in general there may be more than one choice, basically, right, that satisfies all of these conditions. Okay? So there may be more than one way to pick w1 through wm, and each of them will give me different, presumably different upper bounds, basically, right, on the optimal value. So think of it this way. Suppose that I have two upper bounds on the optimal value, okay? So let's say the first choice of w1 through wm, which satisfies these conditions, will give me an upper bound of 100, for instance, okay? And another choice of w1 through wm that satisfies again these conditions will give me an upper bound of 90, okay, 90. So which one would be a better bound for me? 90, of course, is a better upper bound, right? So as a result, essentially, since I'm looking for an upper bound, the smaller the upper bound, the better I am, basically, right? Okay, so as a result, what I want to do is, I want to pick w1 through wm in such a way that I'm going to get the best possible upper bound on the optimal value. Okay? So what do I mean by the best possible upper bound? So I want to actually make this as small as possible. Okay? So I want to push my upper bound, I want to make it as small as possible. Okay? As much as I can. Okay? Why is that? Because after all, I'm trying to find the best upper bound on the optimal value. Okay? So now if you think about this a little bit, well, essentially that sort of turns into the following problem. So I'm interested in finding values for W1 through Wm in such a way that all of these are satisfied. Okay? These conditions are satisfied. And in such a way that I want to make this as small as possible, basically. Okay? Let me repeat that again. So since I'm interested in finding the best upper bound for my problem, okay, so best upper bound basically means the smallest upper bound, okay, so that reduces to the following problem. So I'm interested in finding values for W1 through Wm in such a way that, first of all, they're going to be non-negative. Secondly, they're going to satisfy all of these conditions, okay, and at the same time, this value will be as small as possible, okay, and if I can achieve that, then I'm going to get the best possible upper bound on the optimal value, basically. Okay? Does that make sense? Okay? So the question basically is the following. So how can we obtain the best? And the best means the smallest upper bound. On the optimal value. Well, the answer is actually here, okay? So the answer to this question is the following. So pick W1 through Wm. They're going to be all non-negative. Wm greater than or equal to 0. So that all inequalities given by star are satisfied. All inequalities given by star are satisfied. And in addition, I want this upper bound to be as small as possible. Okay? And W1b1 plus W2b2 all the way up to Wmbm will be as small as possible. Okay, so now this actually sort of brings us to another problem. So how can I solve this problem now? Okay, so how can I find values for W1 through Wm in such a way that, first of all, they're all going to be non-negative, and secondly, they will all satisfy all of these conditions given by star, and at the same time, W1b1 plus W2b2 all the way up to Wmbm, which is precisely the upper bound on the optimal value, will be as small as possible. Now, when we think about this is the following. So now think of the multipliers W1 through Wm as my decision variables. Okay? So I'm actually deciding which variables or what values I'm going to use for my multipliers. And I want to do it in such a way that, first of all, this will be as small as possible. And secondly, my W's will satisfy all of these conditions and all of these conditions as well. Okay? So once again, if you think about this in terms of the following, so think of W1 through Wm as your decision variables. Okay? So you want to find values for W1 through Wm in such a way that they're all going to be non-negative. They're going to satisfy all of these conditions given by star, and at the same time, this will be as small as possible. Okay? So the question is, how can I solve this new problem now? Okay? Well, so if you look at this expression, okay? So if you think of W1 through Wm as my decision variables, well, this is nothing but the linear function of W1 through Wm, basically, right? Okay? If I look at these conditions, again, W1 through Wm are my decision variables. Again, these are linear constraints. Okay? And these are also linear constraints. Well, so then that actually gives me another LP problem, basically, right? Okay? So this gives us the following LP problem. So my objective function will be to minimize this expression. So minimize W1B1 plus W2B2 all the way up to Wm times Bm, subject to, well, I want to satisfy all of these conditions. So W1A11 plus W2A21 plus all the way up to Wm times Am1 is greater than or equal to C1. Then W1 times A12 plus W2 times A22 plus Wm times Am2 will be greater than or equal to C2. And then finally W1 times A1n plus W2 times A2n all the way up to Wm times Amn will be at least as large as Cn. And then each of my W's will be non-negative. So once again, let me just stop here and let's try to understand what we're doing. So we started with an LP problem, which was given right here. Okay? And our question was the following: how can I obtain an upper bound on the optimal value of this problem without solving it? Okay? So without knowing what the optimal value is, how can I actually find an upper bound? So we said that if we take each constraint and multiply by certain non-negative numbers, W1 through Wm, and if we add them up, then that gives us this single inequality. Okay? So up to this point, this is true for every choice of W1 through Wm. Okay? However, I want this inequality to be useful, and if I want it to be useful, then I need to pick my W1 through Wm in a careful way. And by careful, I mean basically they should satisfy all of these conditions, because if they do satisfy all of those conditions, then the resulting inequality gives me an upper bound on the optimal value. Okay? So up to this point, we were just trying to find an upper bound on the optimal value of the original problem. Okay? And then we said that, well, what if I'm interested in finding the best possible upper bound? So the best possible upper bound basically means the smallest upper bound. Okay? So in particular, there may be different choice of W1 through Wm, and all of them will give me presumably different inequalities, okay? Different right-hand side values. So what I'm interested in is finding the best possible choice of W1 through Wm, in some sense, okay? So that my upper bound will be as small as possible. And that's equivalent to solving this new LP problem, basically, okay? If I can solve this new LP problem, then the optimal value of this problem will give me the smallest possible upper bound on the optimal value of the original problem. Does everybody see that? Okay? So here comes the definition. The original LP problem is called the primal problem. So the original basically means the maximization problem that I started with. Okay? So this final LP problem is actually called the dual problem. So now if you think about these two problems, the original LP problem and the new problem, there's some relationship between the two basically, right? So in particular, the new problem arises from the original LP problem. Okay? And secondly, the new LP problem arises from the fact that we would like to find the best upper bound on the optimal value of the previous problem, of the original problem. Okay? So as a result, we started out with an LP problem, and then we sort of wanted to find the best possible upper bound on the optimal value, and that gave rise to this new LP problem. Okay? So the original problem we call the primal problem, and this one we call the dual problem. Okay? And later on we're going to see that there is a close relationship between these two problems, basically. Okay? Before I move on, so any questions so far? Yes?
Can we also derive such relationship for IE problems?
That's a good question. So let me just postpone the answer for now. Okay? So far we're still working with LP problems. I just want you to understand so far what we have been doing. So we're starting with an LP problem. So we wanted to find out an upper bound on the optimal value without knowing the optimal value. And we actually sort of derived the procedure. And then we were interested in finding the best possible upper bound, and that gave rise to another LP problem, basically. Okay? So the original one is called the primal problem, and the new one is called the dual problem. Okay? Any other questions? All right, so now let me try to write this in matrix form. So think of this as our primal problem. Okay? And then I will also write the dual problem in matrix form. Now to do that, what I'm going to do is the following. I'm going to define a new vector that I'm going to call W. And it's going to be given by W1, W2, all the way up to Wm. So this will be an m-dimensional row vector, where m is the same as the number of constraints, okay, in the primal problem. All right, so let's look at the objective function of the dual problem. So what does the objective function of the dual problem look like? I'm taking the first component of W, the vector W, and multiplying with the first component of B. Then multiplying second components, third components, and so on and so forth. And then finally, I'm adding them up. So what does this look like? Well, the objective function of the primal problem, C1x1, C2x2, all the way up to Cnxn, and we can write this C times x for short, right? C is a row vector, x a column vector. So C times x is the inner product of these two vectors, and that's exactly the same as this expression, basically, right? So now I'm asking you, what is the corresponding relationship for the objective function of the dual problem? W times B, exactly. That's what I'm looking for. So as a result, the objective function of the dual problem, the dual which will be a minimization problem, will be W times B. Okay? So W times B is not that it's same as W1B1 plus W2B2 and so on and so forth, which is exactly the same as the objective function. Okay? All right. Now, what about the constraints? So this is a bit trickier. So let's pay attention to the first constraint here. Okay? So remember, my A matrix looks like the following, right? So my A matrix is given by A11, A12, all the way up to A1n, and then I have the second row, A22, all the way up to A2n, and finally I have AM1, AM2, all the way up to AMN, right? So this is what my A matrix looks like, okay? Now let me pay attention to the left-hand side of the first constraint. So W1 times A11 plus W2 times A21 and so on and so forth. So I'm taking W1 and multiplying with the first component here. I'm taking W2 multiplying with this first component here. W3 multiplies the third component. And Wm multiplies the last component, right? Okay? So if you think about this a little bit, well, I'm just taking the inner product of W with the first column of A, basically, right? Okay? So W1 times A11 plus W2 times A21, W3 times A31, and so on and so forth. That's exactly the left-hand side of the first constraint. Okay? What about the second one? Well, I have W1 times A12 plus W2 times A22, all the way up to Wm times Am2. So now I'm just taking the inner product of W with the second column of A. Okay? And finally, if I look at the last constraint, similarly, so W1 times A1n plus W2 times A2n, and Wm times Amn, I'm just taking the inner product of W with the last column of A. Okay? All right, so now how can I express this in a matrix notation? W times A, right? So what does W times A look like? Well, I'm taking W and multiplying the first column of A, and that's exactly the first the left-hand side of the first constraint, basically, okay? And I want this to be greater than or equal to the first component of C, okay? So W times A actually is a row vector, okay? Why is that? Because W is a 1 by M matrix, and A is an M by N matrix, and C is a 1 by N matrix, right? So 1 by m times m by n will be a 1 by n matrix. Okay? So this will be a 1 by n matrix as well. So basically what this expression says is the following. So the first component of this vector will be at least as large as the first component of this vector. Okay? But the first component of this vector is precisely the inner product of W with the first column of A. Okay? And that's exactly the left-hand side of the first constraint. Is everybody convinced that this is true? Okay? Now, in addition, we also have non-negativity on W. So I'm going to simply say that W should be greater than or equal to 0. Okay? So that, again, is a shorthand notation to say that each component of W should be non-negative, basically. Okay? So once again, there's one difference between the primal and dual problems. So in the primal problems, AX is a column vector. Okay, B is a column vector. In the dual problem, WA is a row vector, and C is a row vector as well. Okay, so please pay attention to those differences. But apart from that, W times A greater than or equal to C is precisely the same as all of these constraints, basically. Okay? And indeed, if you multiply, this from the left by W, W1 all the way up to Wm, then the first component will be W1A11 plus W2A21 plus W3A21 and so on and so forth. And that's exactly the left-hand side of this constraint. And the corresponding component will be C1, so the right-hand side will be C1. Okay? Any questions so far? So does everybody see that that is true? Linear algebra, right? Okay? All right, good. Now let me just give you one example, and then we're going to take a break. So suppose that I have the following problem. So I want to maximize 5x1 plus 2x2 plus x3. So this is my primal problem. Subject to minus x1 plus 3x2 plus x3 is less than or equal to 10. So that's my first constraint. x1 minus 4x2 plus 2x3 is less than or equal to 5. And then x1, x2, and x3 are all non-negative. So what I want to do is I want to take the dual of this problem, or I want to figure out the corresponding dual LP problem. Okay? Now, please, again, pay attention. This is really simple. Just think of the procedure that we sort of just described. Okay? So in this case, just exclude non-negativity constraints for now. We have two constraints, right? So I'm going to need two multipliers. Okay, I'm going to call them W1 and W2. Okay, so which means that in the dual LP problem, m is equal to 2, right? So I have only two variables. Now, what does the objective function of the dual problem look like? So think of, for example, that problem. So I'm multiplying the first multiplier with the right-hand side of the first constraint. Okay, so this is B1, right? So as a result, the dual will be a minimization problem. Okay, so I'm going to have 10 times W1 plus 5 times W2. So that's exactly the same as the inner product of W and B, basically, right? So I have W1 B1 plus W2 B2, which is the same as the objective function, right? Okay? All right, so what about the constraints? Now, you should be careful here, because essentially what I'm going to do is, so I want to multiply W1 with the first component of A, and W2 with the second component in the first column. Okay? So note that I'm looking at the inner product of W with the first column of A. Okay? And the first column of A is given by minus 1 and plus 1. So I have minus W1 plus W2, basically. Okay? So minus W1 plus W2. I have greater than or equal to. The right-hand side is equal to C1. What is C1? Well, C1 is equal to 5, basically. Okay? So this is the first constraint of the dual problem. What about the second column? Well, that's also easy. Now you're going to consider the second column, basically. Okay? So you're going to have 3 times W1 minus 4 times W2. Okay? So 3W1 minus 4W2. What is the right-hand side of the second constraint? So it's going to be C2, which is equal to 2. Okay? And finally, I'm going to now look at the third column. So I have W1 times 1 plus 2 times W2. Okay? So W1 plus 2 W2. And the right-hand side value is equal to 1 exactly. And W1 and W2 are non-negative. Okay? So one thing you should pay attention to is the following. If you exclude the non-negativity constraints, okay, so we have two constraints for the primal problem, right? So which means that we have two variables for the dual problem. Okay? So this shouldn't be surprising because I'm defining a multiplier for each constraint of the primal problem, right? Okay? Secondly, the number of constraints in the dual problem is equal to 3, right? The number of variables here is equal to 3. Okay? So which means that for each primal decision variable, I have a corresponding constraint. Okay? So this is the constraint corresponding to first primal variable. This is the constraint corresponding to second primal variable. This is the constraint corresponding to the third primal variable. Okay? So which means that the number of variables is the same as number of constraints here. Okay? And the number of constraints is the same as number of variables here. Okay? Let me repeat that again. So number of constraints is the same as number of variables. And number of variables here is the same as number of constraints here. Okay? Any questions? All right, so let's stop here and we'll continue in 10 minutes, okay?